So let's get started on chapter 11. So most of this I wrote up because there's a lot of little details in it. Go a little faster at the end here. Only a couple sections to go. So this is going to be defining parametric equations. The parameterization of plane curves, or called parametric equations. So a curve is basically defined to be the set of ordered pairs that varies. So this is like your x and your y, and it varies where t is in on some interval. So t is in here, a subset of the real numbers, and it traces out the curve. A couple definitions that we have here are that you have some curve, could do something like this. This is a closed curve, but it crosses itself. And then this is a closed curve that doesn't cross itself. So this is called a simple closed curve. And then if you have just some curve like this that does not cross itself, it's called a simple curve, but not closed in this case right here. So this next definition is the one we really want to use for parametric equations. Let C be a curve consisting of all ordered pairs f of t, g of t, where f and g are continuous on the interval I. Okay, I is a subset of the reals. Then the equations x equal to f of t, y equal to g of t for t and I are the parametric equations of the curve. So this is like the mapping you're doing. You're mapping the real numbers like this, and then you're mapping that to points in the xy plane. It can be defined on some region. Could be entire xy plane is fine. And essentially what it's going to do is trace out a curve. Okay, and it can do all kinds of weird stuff like that. And it has direction. So as you go from left to right like that on t, then this is the curve itself is going to have direction. And we'll talk about that in this next example. Okay, so this next example is kind of how we always get started and try to plot points, essentially, pick values. That's how you always end up doing stuff. We won't be doing it like this in the long run, but so sketch the graph of the curve C that has the parameterization x equals 2t, y equals t squared minus 1. For t, and this is usually what they tell you somehow, for t in -1 to 2. Okay, so sometimes you'll see it written like this. Sometimes you'll see it written like that. I often write like this. It's just easier, usually. The book will have probably something more like that. It just depends. All right, so just set up a table, and I picked values for t that are evenly spaced. You always kind of want to do that for the future stuff you do. So if t is -1, then you just evaluate here and here for your x and your y. So maybe try that on your own and get those values. And then the question is going to be, indicate the orientation of the curve, meaning how is it traced out. So as t goes from left to right, how is the function traced out? So I plotted the points. Here's -2, 0, and then -1, -3/4. That was what, 0, -1, right? And here's all the points that are plotted. Okay, and then the endpoints, I put in the values for t of what they are. So those are the t values, but t is not in this plane here. T is somewhere else over here. Well, not like that, but t is over here that you're plotting, and then you're mapping into this xy plane. Okay, so the next thing we'll do, concept you'll hear and read about, is eliminating the parameter and then sketch. So if you're given x is negative 2 plus t squared and y is 1 plus 2, something like that, then you can solve one of these for a variable and then substitute in. So for this one, you can solve t squared and then substitute in. So you do this substitution right here and then solve. So you end up getting a line. Okay, so it's a line slope of 2. And so if you just graph that line, you just get this, right? You just get the line. But because t varies from left to right, you can indicate what happens to the curve. So let's take a moment to see if it makes sense of how I trace this out. Okay, so how does this work? Does it make sense to you that if t is positive, you go like this in this direction, and then if t is negative, you go like this in this direction? Okay, so look at that, see if it makes sense. Next example, this is a very typical one we'll use for a while in different areas. So given x is a cosine t, y is a sine t, t is in r, where a is greater than 0. Graph and indicate the motion of the point. So what you can do often for these type of questions is eliminate the parameter. So we eliminate the parameter using trig identities. So that was what I was going to say, trig identities. And in this case, you can use cosine squared plus sine squared is 1, and substitute for cosine and sine. So if you solve these for sine and cosine, then you get this form. And then you substitute those in to what sine and cosine are equal. They're equal to 1, right there. Okay, by doing so, you get x squared over a squared, y squared over a squared. You solve and you get this form. So what is that form? That's the circle. The circle radius a centered at 0. Okay. And then how do you trace it out? Well, you pick values of t. You can start wherever. You can start negative if you wanted to, but it's easier to start at 0 and then start increasing with your special angles, right? Pick the ones that work well. And you'll see that when t is 0, you substitute into the function, to the parametric equation. And cosine of 0 is 1, so you get just a. Sine of 0 is 0, so it's right here. So that's where you start when t is 0. So we can actually label that if we wanted to. So right here is what you get when t is equal to 0. That's your value. Right? That is 0a. And then at pi fourths is at the 45 right here. That's when t is equal to pi fourths. Okay, because in both cases you're going to get root 2 over 2, and it'll be basically a times that. So you get that ordered pair. And then at pi halves, you're here. I guess I skipped 3 pi fourths, but 3 pi fourths would be here and then here. And if you just substitute in to the equation, you'll see you get that form. Okay. So next, just take a look at this example. Here's another one. Okay, so I won't work through that one. So check that out. Okay, so that's limiting the parameter, sketching graphs, and orientation of the curve of how it's traced is what we're after there. Okay, let's look at 11.2 now. 11.2 is on parametric equations and calculus, meaning we're going to start taking derivatives. Basically is all we're going to do there. All right, so here's an example of one. Given x is t, this is the same one we did above, right? We can eliminate the parameter. Instead of just plugging in values, we can eliminate the parameter. So we substitute in and we get this function. Okay, and then what you can do is you have an explicit function of x now. Now you have f of x is 1/4 x squared minus 1. And then it's really just evaluated between x now is between -2 and 4 because you substituted here for what t would have been. So that would have been your t between -1 and 2, but t is, as we substituted over here, solved, t is x over 2. So we substitute it in there, and you're good. So now you can take a derivative just straight up, just take the derivative of f, and it's pretty straightforward. Then you can substitute back for your x. So here's your x. Substitute back, and then you get this f prime as t. Okay, so that gives you the derivative with respect to t. Okay, but the problem is it's not always easy to eliminate the parameter. So in that case, we have this theorem. So we're going to use this theorem for smooth curves. This is basically how you can do it. So you have x is f of t, y is g of t, and you want to find the slope dy dx of the tangent line. Okay, so you have some curve, and you want to find that slope of the tangent line like that. It's not a very good example there, is it? Let's try that again. Okay, so we want to find that slope. But we have this defined parametrically, so we have to use other techniques. All right, well, it's easier to, I guess I should say. So this is what you do. You do dy dt on top, dx dt on the bottom. As long as that's non-zero, you're good to go. So let's do this one again. Instead of solving or eliminating the parameter, which is easy to do on this one, we can just calculate dy dt straight up. Okay, so let's do that. All right, so find the slope of the tangent line and the normal line. We'll talk about the normal line. So you do this calculation. So you do dy dt over dx dt. So dy dt, this is just 2t, right? There you go. And the derivative of this is just 2. And sure enough, that matches as the same as above. So check that out. You get exactly the same as before. So that's the slope of the tangent line, like that. And the normal line is just perpendicular to the other line. So those are negative reciprocals of each other. Okay, so like that. Those are negative reciprocals, so they're perpendicular right there. So that's the slope. That's all. I just threw that in just to have us thinking a little bit. Okay, so negative reciprocal. Okay. The second derivative, didn't really go through any of these proofs or anything. We'll do that a little later. Is this, okay, and you'll be able to just apply that formula if you want. I don't know if you can see this example. I threw in another example just to. I'm going to zoom in on it and pause here, and you can copy it if you want to try it. So let C be a curve with this parameterization here. And then here's your questions. Sketch the graph. Okay, and those aren't your theorems, but we just did this and we just did that. Find a function k that has the same graph as C using Okay, so this is then concavity. So this is eliminating parameter, basically. Let me double check that. Okay, well, check it out. So this is a little more sophisticated type of question, and it is something you should go over if you'd like to. Okay, in this section, next section is arc length and parametric equations. So this is defining the arc length formula for a parametric curve. And there's quite a bit here, so we'll just do another video on that. And then we get into surface of revolution as well.